There's a conversation happening right now, under your feet. Not in words, in chemicals, electricity, and sound. A forest isn't a collection of trees, it's a network. And for decades, we missed it completely. Because we were looking at trees one at a time, like they were strangers standing in a room, ignoring each other. They're not strangers, they're talking. And what they're saying might change how you think about every forest you've ever walked through. Let's start with the moment this idea broke into science. In the 1990s, a forest ecologist named Suzanne Simard ran an experiment that shouldn't have worked. She injected radioactive carbon into a birch tree, then checked a nearby fir tree growing in its shadow. The fir lit up. Carbon was moving, tree to tree, through something underground. Not through the soil, through a network of fungal threads wrapped around the roots of nearly every tree in the forest. Scientists call it mycorrhizal fungi. The forest calls it survival. Here's how it actually works. Fungal threads, thinner than a human hair, fuse with tree roots and spread outward, connecting one tree's root system to another's, sometimes across hundreds of trees. It's not a metaphor, it's a literal, physical network, and researchers gave it a name that stuck: the Wood Wide Web. And once you see the network, the behavior gets stranger. Big, old trees, the ones with the deepest roots and the broadest canopy, act as hubs. Simard called them mother trees. A single mother tree can connect to hundreds of smaller trees through the fungal network, and when one of those smaller trees is struggling, shaded out, sick, starving for sugar, the mother tree sends carbon directly to it, through the fungus, on purpose. That's not an ecosystem quietly existing. That's resource allocation. That's triage. But sending food is the easy part. The forest also sends warnings. When a tree gets attacked, say by aphids, it doesn't just defend itself. It releases chemical signals through the air and through the fungal network below ground. Neighboring trees pick up the signal and start producing defensive compounds before the aphids even reach them. They're not reacting to an attack. They're reacting to a warning about an attack that hasn't happened to them yet. Acacia trees in Africa do something even faster. When giraffes start browsing their leaves, the acacia pumps tannins into its foliage within minutes. Tannins that make the leaves taste bad and, in enough volume, turn toxic. But here's the part that sounds like science fiction. Nearby acacias, untouched by any giraffe, start producing the same tannins minutes later. They smelled the warning on the wind, ethylene gas, and acted on it before the threat ever arrived. A tree, defending a tree it's never touched from a danger it hasn't faced yet. Then there's the part almost nobody talks about: sound. In 2017, researchers in Australia recorded faint clicking noises coming from inside plant roots, rhythmic, around 220 hertz. Roots placed nearby bent toward the sound. Nobody's calling this talking in the human sense, but it's vibration, used as information, between living things that have no nervous system. That alone should stop you for a second. So why does this matter to you, specifically, standing in a forest with headphones on? Because for centuries, we've measured forests in board feet and acreage, units of extraction. Cut it, mill it, move on. But a forest behaving like this isn't a resource sitting still, waiting to be used. It's an organism. A single dying tree can trigger a cascade of chemical alerts and resource transfers across an entire hillside. Clear-cut the wrong section, and you're not removing trees. You're severing a network that took centuries to build, and that the survivors may never fully recover from. And this changes the math on something else: old-growth forests. The oldest, biggest trees aren't just carbon storage and pretty postcards. They're the hubs. Remove the mother trees first, which is exactly what selective logging often does. And you don't just lose lumber. You sever the network at its most connected points, like deleting the busiest servers in the internet and wondering why everything slows down. This is still an active, contested area of science. Not every researcher agrees on how much intention to assign to any of this. Whether warning is the right word or just chemistry doing what chemistry does. But the data on the network itself, the carbon transfer, the chemical signaling, the speed of the response, isn't in dispute anymore. The mechanism is real. The only argument left is what to call it. So here's where that leaves you. Next time you're under a canopy, you're not standing in silence. You're standing inside a conversation that's been running for longer than any human language. One that moves through roots instead of air, in carbon and chemical signals instead of words. We spent thousands of years assuming trees were the most passive things in nature. They might be one of the most connected. And the unsettling part? We only found this because we finally bothered to look underground. Which raises an obvious question. What else, right under our feet, have we been ignoring?